What is data imbalance in ensemble frameworks? Imagine trying to find a needle in a haystack where most of the hay is the same color and only a few pieces are different. That's similar to what data imbalance looks like in machine learning. It happens when one class in your data has way more examples than another. For example, in fraud detection, most transactions are legitimate, but only a tiny fraction are fraudulent. This uneven distribution can cause problems for machine learning models, especially ensemble methods. Ensemble methods are techniques that combine multiple models to improve predictions. They include approaches like bagging, boosting, and random forests. These methods work well because they pool the decisions of many models, making predictions more stable. But when data is imbalanced, these models tend to favor the majority class because it appears more often. This means they might miss the minority class, which is often the most important, like detecting fraud or diagnosing rare diseases. To fix this, data scientists use different strategies. One way is to change the data itself before training the models. This can be done by oversampling, which means copying or creating more examples of the minority class. Synthetic data generation, like creating new fake examples that look real, is also common. On the other hand, undersampling reduces the number of examples in the majority class, balancing things out. Sometimes, combining these methods with ensemble techniques like bagging or boosting helps the models better recognize rare cases. Another approach is to change the way the algorithms learn. Cost-sensitive learning is one example, where mistakes on the minority class are penalized more heavily. This makes the model pay more attention to those rare but important cases. Adjusting the objective function in ensemble algorithms can also help them focus on minimizing errors on the minority class. Variations of boosting algorithms, like AdaBoost, can be tailored to handle imbalanced data better by giving more weight to misclassified minority examples. Sometimes, combining data-level methods with algorithm tweaks gives the best results. For instance, resampling the data and using weighted loss functions together can improve how well the ensemble recognizes minority classes. Advanced techniques include using multi-objective optimization or evolutionary algorithms, which help find the best balance between different goals. In image recognition, deep learning ensembles that incorporate resampling and weighted loss functions have shown promising results in handling imbalance. While these methods improve performance, they also make the training process more complex and computationally demanding. Choosing the right mix depends on your specific dataset and what you want to achieve. Understanding data imbalance in ensemble frameworks is important because many real-world problems involve uneven data. Recognizing and managing this imbalance helps create fairer, more accurate models that can detect rare but vital cases. This is especially true in applications like medical diagnosis, fraud detection, and image recognition, where missing the minority class can have serious consequences.